Let us look at another enthalpy problem. So bomb calorimetry, we already talked a little bit about how delta H is more of a total enthalpy, whereas the Q is more of how is heat transferred. Another way of thinking about it is we have constant pressure. So in a bomb calorimeter, your pressure is contained. It's not like you can escape and depressurize the outside of the containers of the bomb calorimeter. You can't make them be bigger like you can the outsides of a balloon. And so it maintains a constant pressure within that calorimeter. And so in these types of situations, you have the heat transferred within the reaction is being transferred to the water and back and forth. And so you've got your system and your surroundings, and that heat is traveling very easily between the two. But what makes this so nice is within your calorimeter now, you're able to tell how much heat was produced by the reaction. And that's the whole point of these problems, is being able to set up a system that allows us to tell how much heat was released or how much heat was absorbed by the reaction that we're studying. If you can think back at the history of this with bomb making, that's a very important concept to consider. You want to know how much energy your bomb is releasing, and so hence its name, bomb calorimetry. So in this problem, we're going to do a heat of neutralization reaction that's very similar to what you will see in the laboratory. And so for these problems, we're trying to calculate enthalpy, which is going to be Q of the reaction. So here is our setup. Instead of having a fancy calorimeter like you might have seen other pictures of, we're going to do what's called a coffee cup calorimeter, where you use styrofoam cups to simulate the calorimeter. Because styrofoam, it's a really good insulator. So we're going to use styrofoam plus a thermometer plus a reaction that's going to be inside of our coffee cups, and we're going to see if we can't figure out how much heat is released whenever sodium hydroxide and hydrochloric acid react and thus neutralize. Alright, so here is all the setup for our experiment. Let's pretend this is what happened. We measured a coffee cup, all of the goodies that come with a coffee cup, and we determined the weight of it, which was 12.573 grams. Then we combined sodium hydroxide and hydrochloric acid into the styrofoam cup. The mass of these plus the outside coffee cup was 97.623 grams. We're going to assume a specific heat of 4.017 joules per gram per degree Celsius for this reaction mixture. So what's going to happen is that as the sodium hydroxide and the hydrochloric acid react together, they're going to start to heat up the temperature within that styrofoam cup. And so initially it might have been at somewhere around 23.2 degrees Celsius, and my final temperature was at 43.6 degrees Celsius. And so I can ask the question, what is the heat of neutralization, or the enthalpy, for this reaction? And this is just a typical setup for these calorimetry problems. You have everything you need to know to answer lots and lots of questions about the reaction and the enthalpy that's occurring within that reaction. Before we go any further, let's go ahead and highlight some of the variables that we are interested in. We know the mass before and the mass after, so that's going to tell us our mass of our reaction. We have some volumes and molarities, and you know why that's important, right? That'll allow you to calculate your moles. And then we have a specific heat, we have an initial temperature, and a final temperature. And all of these variables are going to be important when calculating this enthalpy. Alright, so let's determine Q. If we know our specific heat, that is our variable of S. Our mass initially was 12.573, and our mass final of the coffee cup plus the contents was 97.623 grams. So if we subtract those two values, that's going to give us the mass of only the solution that was inside of our coffee cup, that of 85.050 grams. Our initial temperature was 23.2 degrees Celsius, and our final temperature was 43.6 degrees Celsius. So we can subtract those values to give us a change in temperature of 20.4 degrees Celsius. At this point, we need to stop and make sure all of our units are going to cancel out. Grams are in specific heat, and the mass is also in grams. The temperature is in degrees Celsius, and our specific heat is also in degrees Celsius, leaving us with joules for Q, which is what we want. So let's work this problem together. Our Q is going to be equal to our specific heat, 4.017 joules per gram degrees Celsius, times our mass, which is 85.050 grams, times our change in temperature, which is 20.4 degrees Celsius. If we multiply all of those together, our grams are going to cancel and our degrees Celsius are going to cancel, leaving us with just joules and a total Q for this reaction of 6,969.575 joules. I'm going to go ahead and leave all of those digits here. We don't want to round anything until the end. Now, of course, we'll want to correct for sig figs at the end of this problem. But this is our Q at this moment. But we don't quite have the whole question answered because this is the enthalpy for 85.050 grams. It's more useful to figure out how much heat of neutralization was released per mole of our reactant. And so because what are the odds that somebody else is going to go in the lab and measure out exactly 85.050 grams? It's not. And so you want to make it per mole so that other laboratories can compare and contrast your value with what they received. So to do this, we have to think about what is the reaction that's taking place. What is this heat of neutralization? What's my neutralization reaction? All right, so let's write a balanced chemical equation first. We have sodium hydroxide plus hydrochloric acid yields, what does it yield? Break those into ions. Your sodium is going to react with your chlorine, and your hydrogen is going to react with your hydroxide to yield sodium chloride and water. So that's my balanced chemical equation, and notice it is 1-to-1. Now what do I do with my volumes and my molarity? Remember, molarity equals moles per liter. So volume times moles, molarity is going to give you moles. So let's do that for each of these problems. 3.00, and why I'm doing this is I'm trying to figure out which one's my limiting reagent, because then I can determine my heat of neutralization per mole of reactant. And notice one of them is obviously going to be my excess because I have the same concentration for each of them. But let's convert each of these into moles. So I have 3 molar times my volume, and remember this is in milliliters and molarity is moles per liter, so I need to turn that into liters before I go further. And that is going to give me 0.123 moles of my sodium hydroxide. Similarly, you can do the same thing for hydrochloric acid, multiplying the molarity in times your volume in liters to give you 0.12 moles of hydrochloric acid. So these are things I know, and I know that it is 1-to-1. So because of that, that tells me my limiting reagent is going to be my hydrochloric acid. So what do I do with this? All right, I know that I have 0.120 moles of hydrochloric acid, and I know my Q for the total amount of solution that reacted. But I need to know how much energy was released per mole of reaction. And remember, if we go back here, how many moles of hydrochloric acid are there per each reaction? There is 1 mole per each one reaction that takes place. So because of that now, I can simply take my Q, 6969.575 joules, and I can divide it per the amount of moles that reacted in my coffee cup. If I do this math, that's going to tell me I get 58,079.79 or 80, and that is joules per mole. Let's go ahead and convert this to kilojoules. There are 1,000 joules and 1 kilojoule. So how much is that? And let's correct for our 3 sig figs here, because is that the right number of sig figs? Yes, we have 3 sig figs right here, 1, 2, 0. So 3 sig figs. Let's correct that. So that would be 58.1 kilojoules per mole, and that is my enthalpy of my reaction, also called my heat of neutralization.